All right, so welcome everybody. It's a great pleasure to have Pranay Gorantla here. He's going to give us a set of 3 lectures, the Tata Emphasis lectures. Today is his first lecture, and so he's going to tell us about kinematics of exotic field theories, symmetries, and dualities.
Yeah. Thank you, Omkar, for the introduction. So, I'll be talking about exotic field theories, in particular symmetries and dualities today. So, it will be more like an introduction to one particular exotic field theory today. As a motivation, these field theories were people started studying these things because of closure of exotic lattice models, including the platform models.
Yeah, I cannot hear you. I mean, I'm not getting your audio.
Yeah.
We have our usual aircraft noise.
Yeah. Let's wait for a couple of minutes.
No, that's fine. Sulama. Yeah.
School was cancelled.
Yeah.
Not like this. Yeah, not.
What's the probability we end up next to each other? The master can.
What is the fractional benefit to others and to yourself wearing masks?
I'm told to yourself there is a distinct benefit.
But somehow I think that if you sneeze and you keep the mask on when you sneeze, that's a huge benefit. Because that's dominant mode of spreading. Of course, I see most Indians, they take the mask off, sneeze.
Is that evidence that he drove somebody to the airport with a mask and never got COVID? And then on the return, the same guy was driven back by somebody. The next day, without a mask, and that guy got COVID, etc. Thereby proving.
Students studying at ISI.
He's a string theorist. He has no idea how to deal with data.
Is it? Am I audible now?
Anybody from the Zoom audience?
Yeah.
Yeah, it's audible now.
Okay. So okay. Maybe we can. Oh, yes. Okay. So I'll be talking about kinematics of some exotic field theories today. Symmetries and dualities. This is a work based on. This talk is based on the work with Pota and Mati and Shubham. Okay, as a motivation, I just wanted to say that exotic models, lattice models, and fractal models have been like the rich subject in the past 15 years or so. People have been working on it more, and these models, although they look very decent at the Hamiltonian level on lattice, like they were just local interactions, the long distance physics is very non-trivial and it's not captured by any standard continuum physics. So that's why we need to go beyond standard continuum physics and go to this exotic. So before getting to the exotic theory, in all these talks I've been just mentioning some phenomenology of these models, but I never really showed any particular model. So I just want to quickly show a particular model where you can see this kind of physics. First, let me review Dolly code. So let me quickly go through this. The Hamiltonian is given by this. There is a Z2 spin at every length on the lattice. I'm assuming a square lattice. And so there is a poly Z operator and X operator on the lengths. And the Hamiltonian is given by this, where the AB is a term defined at every point. The product of all X's. Was there a question?
I'm Zahid. I'm not getting your audio actually.
Is anyone else on Zoom have the same trouble?
I think
I think
Zoom participant having this problem.
I think the audio is not completely clear. Maybe Pranay, you have to be a little bit louder, maybe, and then it will be okay.
Speak loudly.
Okay. Can you hear me now?
Yeah, this is better, at least for me.
It's not too uncomfortable. Okay, is this better?
Yeah, this is better. This is good.
That's fine.
Okay, so first I'll just quickly review the body code. So it's a term at every vertex given by the product of the poly X operator and the length of the vertex. And there is it's the product of the poly Z operators. Next thing about this body code is it's exactly solvable because each of these terms comes in. So it's completely solvable. Simultaneously diagonalize all of these. The eigenstates define the spectrum. For example, the ground states are given by those states for which the values of A, B, and B are all ones. Okay? And the excited states are like those where some of these ABs are eigenvalue -1 or some of the BPs are -1. And these excitations are called P and 1 and now I want to quickly talk about what happens when you act on these states by poly Z operator or a poly. Okay, let's consider an E anion, like a state which has an E anion at this vertex. And let's
Just because I forget, the Z is the magnetic flux and the X is the electric output. Which one was the vertex and which one was sorry? I just forget that.
So the blue ones are the X poly X operator. So
The Z's
so this is the magnetic flux.
This is the magnetic flux. Thank you.
Okay, so let's apply the poly Z operator on this length next to the angle. And then we get this length. But then we can check that the eigenvalue of AB at this vertex is not -1 anymore, it's +1 because of this Z operator here. But on the other hand, at this vertex, it's -1. So you can interpret this as the E anion moving to the next one. You can do the same thing for the M anion. You can operate on this length by the poly X operator, and the resulting state would be so it's like you can interpret that as an M anion moving.
So why are the anions living at vertices and plackets? Because that was defined as eigenvalues of A operators.
So yeah, this one is the eigenvalue of A operator which lives on the vertices.
Surround them.
The red guy is an electric charge.
Yeah.
And the blue guy is a magnetic flux.
Yeah, that's right. And then we can look at when you place this theory on a torus, like instead of an infinite lattice, there are more operators that you can construct, which are these logical operators, which is product of Z's around these lengths or product of X around these lengths. Okay. These operators also commute with the Hamiltonian. In fact, they commute with all the ABs and BPs, all the terms. So you could also simultaneously diagonalize these things. But however,
Excuse me, sorry, Pranay. Your voice is not clear completely. I mean, it's clear in bits, but then I think we are losing some some of your voice in between.
And we get the other because this is the lower level. Wait, she did.
This one easier.
Like this.
Yeah, maybe is it better?
Is it better now?
Yeah. Right now it's better, but as you're speaking, some parts of the sentence are getting chopped off.
Oh, can you hear me now? Is it better now?
Yeah. This.
So now we have these W's and W as four operators, and we can simultaneously try to see whether we can diagonalize them. But the thing is, the W and W tilde operators don't commute with each other. So they satisfy these commutation relation values. -1 is the thing, which means they don't count. So we can't simultaneously diagonalize all W's and W. That's what we can diagonalize one set of them. So let's say we diagonalize WX and W. So in this case, we can ask what the ground states look like. What are all the ground states? So let's say we start with a ground state which has eigenvalue +1 for both Wx and W1. Then we can construct 4 other states, which are these three other states, which are these 3 here, and they carry different set of eigenvalues for Wx and W. For example, this one carries eigenvalue -1 for W1. That's because of this commutation relation. Okay. And similarly, the other 2 states. So there are like 4 ground states on it all. This fact is what?
Corresponding to the 4 values of the Z2.
Exactly. Yes, that's right. So yeah, this theory, if you want to
just so ignoring these autonomies for a moment, the electric operators and the magnetic operators, if you diagonalize them completely, this is a complete set of commuting observables. The eigenvalues uniquely labeled eigens. And now you're saying on a torus, in addition to these, the complete set of commuting observables includes one of these.
Yeah, one set of these. Like either the W's or the W.
Okay, so one set and W squares to one.
In this case, squares. So 0.
So I see. Okay.
So the complete set of observables will be this and this and this. Okay. That's one shot. So let's say we are interested in just the low energy theory. This theory is gap. Clearly, all the excited states have like finite energy. So if we focus only on the low energy part, which includes only the ground states, and that's described by the C2 gauge theory +1. But this one here, it's a VF type action. Okay, where A tilde and A are U1 gauge. So you can embed the C2 gauge theory using U1 gauge. You can also think of it as the mutuals and chance cycles.
Sorry to be
Yeah. Yeah.
So how do you embed it in? So this is a standard U1 transaction.
That's right.
And so some subgroup of the discrete subgroup of that is your C3.
Yes.
And then is there a way so then you flow just
Yeah. If you look at the equation of motion of A tilde and A, it tells you that both A and A tilde are flat.
yes,
So the only information is in the holograms.
right. But then why isn't it a U1 set of holograms, etc.? Let's say down to C2.
Yeah. It can't be U1.
Oh, I see. Because it's VF, because it's
Yeah.
then I see. It's literally that this maps to it.
Then the low energy. Yeah. In fact, you can map the logical operators on the lattice, on the torus, to the hologram steps.
So only the C2 concept.
Yeah.
I think you can talk about this theory in other contexts as U1 times U1 gauge.
You can.
Somehow in low energy is only the C2 concept.
That's right. Yeah.
Is it probably thought that K is
Yeah. K is 2. Yeah. And it has only off diagonal. Yeah. It doesn't have that.
I think it's just a statement that there are basically 2 primary operators, right? So that count the number of ground states, even the U1 thing. Count the number of ground states. It's how much it's K. K. So that's 2, yeah. Oh, but there are 2 of them.
Yeah.
So therefore.
Yeah.
Sorry.
So let's take a U1 theory. Level K. Take it on the torus. It has K ground states, right? Because it has AX, AY, their position and momentum, they commute with each other. They're both periodic. You know, that's that usual story. So the K ground states, right?
There is also a general story, like if you have 4 E1 gauge fields and you have a K matrix, and the ground state degeneracy is the determinant of K.
So the statement is that the ground state degeneracy of this human theory matches that.
Exactly.
But is there any equivalence in terms of excitation?
But it is that okay. So those are the bits. So you might wonder what happened to the excitation because we are focusing only on the ground states. But they're captured by the defects in the field. So far we looked at only the Wilson line operators, which are at fixed time. But then you can look at defects extended in time, right? Like this A0, the temporal component extended in time. So they would capture the E and M.
I'm sorry to be very stupid. Suppose I diagonalize this. I can write this as a U1 theory, an A1D A1 with K, and an A2D A2 with minus K, right?
That's right.
Okay. Where those Ks would each be 2.
Yes.
So is that a diagonalizable matrix?
I think
Just 2 on this one side.
2, right? Because it's ADA.
Yeah, it's a metric. Yeah,
Maybe 1 point. Yeah, right. Or maybe 2 because okay, 1 minus 2.
I think it's 2 minus 2 because he has 1/2 point. Normally there is a 1/4 point. So actually there is a 4. Okay.
Yes.
Degeneracy.
So now if I think of it this way, I've got 2 decoupled U1s. Okay. And I would have thought there that I had 2 operators, each of which commute with each other. Namely the holonomy of the first U1 and the holonomy of the second U1.
that's right.
So how come you're getting? But I'm trying to match this with what you said. The compute set computing observables versus computing.
There is one issue though when I diagonalize it that way. You see, when you the linear transformation that you do involves a matrix which is not an integer. So the periodicities of these matrices don't match up.
So you're saying that's not equivalent. It's not equivalent.
I don't think you can do that.
I see. Even though both will have 4 states.
That's right.
These are different.
Yeah.
At the operator level, you get different operators.
Yes, that's right.
I mean, he was saying the diagonalization I did was not. You're saying that if you quantize this theory, you get some set of operators, the operator of 4x4 matrices.
Yes.
You get some 4x4 matrices. You quantize the theory I was talking about. You also get 4x4 matrices, but these are not similarly.
So yeah, the excitation
Is that correct? Because there are other groups who describe this Z2 spin liquid ground states using these doubled Chern-Simons theories with level K and minus K. And then the degeneracy is K square.
yeah, the region is I don't think
and also it is a Z2 spin.
Yeah.
Not U1.
I'm not sure if the operator content matches because the holonomies won't be the same. I don't have a better way to say it, but mathematically, what I think of is to preserve the 2π periodicities of all these things. That ultimately, there are transition functions and have to be 2π periodic. Preserve that. Any transformation you do should be like an integer matrix with determinant 1. Here, I don't think that's the case when you do this kind of transformation. So at the level of Lagrangian, you would get something similar. So locally, things would be similar, but the whole point here is like the global structure. That would be very different.
Thank you.
So yeah, as Sandeep asked, what happens to the excitations and they're captured by the defects. And the mobility that I was talking about is just the fact that we have the spatial regions which can move these defects. So the defects can bend. So you should really think of the this support of the defect as the trajectory of the excitation. Okay. So the red one is for the EN one, and the blue one is for the MM.
So just the standard Wilson lines.
Yeah.
Correspond to your defects.
Yes. Yes. So the low energy theory captures the excitations as well. They're captured as defects because they have infinite energy in this thing. Yeah. Next, let me describe arXiv model. I described arXiv because arXiv is very similar to that, at least at the Hamiltonian levels. So this now it's also a stabilizer code. So every term in the Hamiltonian comes with itself. The terms are these. There are 3 terms associated with the vertex. So at any given vertex, you take product of the poly x operators in the yz plane or the xz plane or the xy plane. These are the 3 vertex terms. And then there is a term corresponding to Q, which is the product of all the poly z operators on the links around Q. So we still have Z2 spins on the links. That did change.
I'm sorry, Aaron. You said you created in the old one. You said you created these p anions and the p anions by acting with some sigma operators.
No, you can't. Yeah. So although I talked about this, there is no local operator that can create just one p.
Because local operators are single, right?
Exactly.
Okay.
Yeah. So for example, if you just act, let's say here by the ZL operator, it creates 2 E anions here. And you should really think of this E anion as 1 E anion plus some line going in some direction.
And tell me the definition of the E anion is what, please? At charge 1.
AV is just -1, and that works.
So there is a state in the theory that has this okay? Yeah. But there's no operator that
There's
creates
no.
it.
Yes.
So should I think of the state as not being gauge invariant or something? The state is just one anion.
Yeah, I think it is. You just have to add a line. Then
fine. So you should think of it not as local, not like the type.
It would be like sometimes.
Yeah, but I think his point was that these are not states that can be created by the local operator.
Yeah.
Whereas
John Simon say also you can create a line sometimes. Just a single charge.
Excuse model. So these are the terms. You can see easily that each of these terms comes with each other. For example, let's look at this term. Let me put that here. There are always like 2 links that they share. So the minus that you get from these 2 links will just cancel. So they always come with each other. But more importantly, note that the product of all these 3 A's is 1. That's kind of clear because when you take the product of these 3 terms, you always have square of a poly operator that. Yeah. That will be. And since A's and B's they commute with each other again, once again you can just simultaneously diagnose all of this. Okay. And then yes,
true. So the A's are still defined at each vertex.
Yes.
And the B is on
the cubes.
So that you will in the space in 3 dimensions.
Yeah, this is in 3 spatial and yeah.
Okay, I'm with you.
Okay. So now the ground states are once again where A's are all 1, B's are all 1. Because I should have mentioned this, there is a minus here. That's why we want A's and B's to be 1. That will be the state of the lower symmetry. Okay. Now let's look at some examples of excited states. So one example would be where both AX and AY, the vertex are -1. Thing is, you can't have just one of them being -1 because of this product relationship. You have to have at least 2 of them -1. So let's say those 2 are just AX and AY. This is what I would call a Z line, and I'll explain this terminology soon. And the other kind of excitation would be B equal to -1. Then there's no problem. You can have this excitation. So that's called a fact. Let's see why they are called binomials of fractals. So consider, let's say you have the Z line, which means AX and AY are -1 at this vertex. And look at this thing here. I'm assuming that the vertical direction here is Z, and I'm ignoring the X direction. So we have the YZ plane. And if I apply the poly Z operator on this line, the resulting state would be equivalent to Z line at this vertex. So a Z line can move in the Z direction. There is an operator which can move it to the Z direction. On the other hand, if you apply a poly Z operator on this line in the Y direction, what you observe is that the resulting state has an LX here and an LY here. X line on here and a Y line. Okay. The reason is simple. the product of these Lx, Ly, and Lc is 1. What this means is if you have all these 3 excitations at the same point, it's as if there is no excitation there. It's just as if all the A's are 1. Using this fact, this just follows from the fact that the product of all the A's is 1.
Lx, no.
Lx is the symbol I use for the excitation. So it's a state, it's an excited state, which means so Lc means Ax and Ay minus 1. Okay. So when you have all 3 excitations at a position at a single vertex, that just means all the A's are plus 1. So it's as if there is no excitation there. Right. But using this fact, we can write Lz as Lx times Ly. You can think of a Z line as a product of X line and a Y line. And the Y line moves in the Y direction. That's what happened. In general, Li line can move only in the XI direction. This is the first kind of mobility constraint.
I'm sorry, was there a reason you took 2 of the A's to be minus 1 instead of 1?
Yeah, that's because the product of all the A's should be 1. You can't have just one of them being minus 1.
You're right. That wouldn't be it.
What if you act by some other polynomial? It's not but X
X doesn't do anything to this.
doesn't do.
Yeah, because these are Lx, these are AV. And AV involves only the X operator. So when you apply X, it just commutes. Doesn't change the eigenvalue of A. Changes the eigenvalue of X. So it creates some fraction. But that's what we'll look at next. Let's say now I'm assuming that imagining the 3D system and you have a fraction in this cube, the dark black cube. Okay. And I apply a poly X operator along this line. What it does is the resulting state is equivalent to having 3 fractals in these 3 other cubes, the adjacent cubes. These 3 cubes share a link with this original cube. So what this means is, in fact, you can try with several other operator structures and you can never move this particle to another state which has only 1 fractal. You'll always create 3 or more fractals.
Fractal is this
excitation. Yeah. This cube excitation. Excitation of the cube, where the B is minus.
But sorry, you can apply more things than reduce the number and again create 1 fractal.
No, you can't. That's it. The minimum you can do is 3 if you are away from this bucket. The only way you can get 1 is if you come back to this. There is no way you can create just a single excitation anywhere else. Single fractal excitation. So that's why it's called fractal. It just cannot
being by local operator.
by local operator space.
This can move in any direction. I mean, it can split in any direction.
Any direction. So I showed here like in the XY plane, but you can do it in other directions. And yeah, you'll just keep creating more and more excitation. But you'll never be able to create just a single excitation anywhere else.
And you use non-local operators, you can do anything.
I think so.
Because, sorry, if I understand, XL squares to 1.
Yes, yes.
If I apply it again, the 3 will come back.
Yes, exactly. But it come back to the original position. It hasn't been. Yeah.
An example of a non-local operator would be just the graph where the fractal is here and again where the fractal is there.
Yeah.
That
Clearly exists.
Yeah, whatever. So, yeah. So yeah, that's what people mean when they say big fractal. This is the restrictive mobility.
And then, so if you want to move it, you have to proliferate.
Yes.
So the Hamiltonian, if you add a complicated Hamiltonian, it can be complicated local Hamiltonian, can be.
Yeah. So then you can look at the logical operators. I won't discuss them like that. Actually, kind of similar. For example, you can take the product of z's along the vertical line, the horizontal line, or the x direction. So those would be one set of logical operators. The other set would be consider product of all the x operators in a plane. So that it's called the membrane operator because it's like in a plane. Plane meaning like take all these planes in the xy plane and take the product of all the poly x operators in that plane. That would be the another logical operator. So these 2 logical operators again don't commute with each other. You can try to diagonalize them, and then the number of ground states goes like this. If you put this system on a torus, like I'm imagining a torus. So the ground state degeneracy goes like this. It's like a huge ground state degeneracy. It's not extensive. It's not like to the volume of It's just true to the linear side of the system.
I missed these logical operators. So one set you said was just this Wilson line kind of things.
Yes.
And this Wilson line is conserved, so it doesn't matter where you put it. If it's mapping the exact direction.
It does matter, actually. Yeah, you can't move them.
Okay.
So in the Java code, the way you can move them is by just multiplying these stabilizer terms, like the terms in Hamilton. You can multiply them and you can just move it. Because the stabilizer terms are just one in the ground. But in this case, we don't have a term which can deformate that. So these are not the two options.
Okay.
Yeah.
Okay. And so then there's one for each sort of location on the plane.
Yes.
So that sounds like L square, Lx, Ly such operators.
Okay. There is still a constraint on these operators. Let me see. Yeah, let me get back to it. I don't remember it exactly, but there is a constraint on these operators.
So actually, it's only Lx or Ly.
Yeah, actually, it's just Lx plus Ly.
That's the exact sign.
Yeah, it's clear why these are just Lx plus Ly because there is a membrane operator. These operators.
They just describe that operator. You've got a plane, and then let's say XY plane, and it links in Z direction.
Yes, links in the Z direction.
X-ism.
Yeah, sigma X. Only X operator on all these links, which are in the XY plane.
Yes, and then there are LZ.
LZ of them, and similarly in the other two.
That's clear.
This is clear. Yeah. So in the other one, okay, I don't remember exactly how it goes, but yeah.
There's some constraint.
Yeah, there's a constraint.
And big cut down.
Huh?
It's a big cut down.
Yeah,
Square
it is a cut down. Yes. And that's what leads to this blockchain dependency, which goes linearly in the system sense. And you can then ask, like, what is the low energy description of
Sorry, it's 2 to the power 2. So one set comes from these fracton operators, from these operators, the others.
Yeah, that 2 you can think of it as in the atomic code also you have 2 square. Yeah, one set from the fractons and the other. Yeah.
Sorry, Pranay.
Yeah.
Almost. I would be managed from string theory 7 fast.
Yeah.
Is there any chance or any discussion that in condensed matter like system we can realize these?
In a holistic system, I don't know.
At least for the Turing code, I know there is some Turing code.
Because
This is what will come later.
So the low energy theory.
Just one more. Yeah. In the previous thing, I was thinking of this as some version of a gauge theory with charges and fluxes. Am I allowed to think of this thing also like that?
Yeah.
These are monopoles.
Yeah, you can think of there's fractons, you can think of them as monopoles, and there's linos, you can think of them as electrical acceleration. And in fact, it's captured by the tensor gauge field. These are not like the TIFR gauge fields. So this is where the tensor gauge field is coming.
That's why there are 3 kinds of charges.
Yeah, exactly. I'm not describing it here, but it involves gauge fields which are exotic gauge transformations. They're not like standard gauge fields.
So why is it that the tensor has 3 types of charges?
It has more than one kind. I was saying the normal gauge has only one kind of charge. I was going to ask when he said that it was not the gauge theory, how come you have so many charges? So some different kind of.
In fact, you have like Lx plus Ly plus Lz charges, not just these many charges. And that's why it's called a subsystem symmetry, because each plane you have a symmetry. You have a charge of symmetry of. Yeah.
Sorry, this will be aside the issue, but tensor gauge field doesn't just mean higher form base.
No. Not field form. It's symmetric tensor. No, symmetric stuff. Yeah, these are symmetric tensors. Yeah, that's why it's not a standard EQFT, but it still looks like a BF type action between 2 set of tensor gauge fields. In the Tauric code, it turns out that these 2 were kind of similar. They are like here, you can exchange E and M, and it looks very similar, but here it doesn't. And you can see that already in the mobility. There are line outs and there are patterns. Very different mobility. So it's not self-dual in that sense.
So sometime back, maybe Shukra Bhattacharya is there, can fill it in. But there was some proposal that even holding a piece of paper, it creates factors because these pieces you create have exactly those same properties. They don't move, they go only along straight lines or the boundary, and they cannot terminate. It's like that. But at every termination point, you get So is that right, Shubhra, that there are condensed matter examples apart from this paper folding one, which I happened to hear by accident?
Is Shubhra here?
I heard his voice in the beginning, so without seeing his name. He would know probably.
Okay.
But you agree, right? So that you might have heard of this.
I didn't hear of that.
There is some work which, for example, here, Roderick Meissner and Vijay Shenoy did. And Vijay gave a talk here in our seminar series, which interpreted these simple pieces in paper folding as fractals. And he introduced the selected distance again.
Okay.
Yeah, I remember talking about this.
You were there in that talk?
Not here, one of the street people.
He went there and gave the same talk.
I mean, use Zoom. So this could be a U1 theory also.
Yeah, in fact, the tensor gauge fields that I use here are like U1 gauge fields, but then I write a weird type action which makes them effectively Z2. It's exactly like how I call there's a Z2 gauge field.
What is the gauge transformation problem?
So there are set of gauge fields. This one transforms normally. There is an Aij, where I and J are not equal. So AXY, AYZ, and AZX, which transforms as A plus. Then the other side is more not trivial. I'll write it down, but I don't know. I don't expect it to be this one.
So what are these now?
Yeah, these are some other kind of exotic tensor gauge fields. These are not even like this one.
So this is not the model that you're talking.
This is these are the two sets of gauge fields that go into this BF type.
Oh, I see.
That is not very good. It's very ugly. But the one set of gauge fields is this here. These are like the typical tensor gauge fields that we have. The other set is very different.
There is some other phenomenological description based on like what you conserve, whether just charges or charges and dipoles.
Yeah.
So that is also naturally
not in these gauge fields, but we have to include AXX, AYY, AYZ, all the possible symmetry. Then comes into a dipole gauge. In fact, I gave a talk about that. Yeah, that was like dipole gauge.
So your model looks like it had an XYZ sort of symmetry.
Yeah.
But your gauge fields are singling out one day. A0 is the Z direction.
No, it's AIJ on this picture. Yeah. So this Z2 times Z2 subsystem symmetries. Like there are Z2 subsystems with fractals and Z2 subsystems with the Lano. They don't compute with each other, just like in the Nori code. That leads to the ground state we didn't see that. And the excitations are captured by defects of these gauge fields, like for example, the gauge field here A0. You can write the exponential of I A0 in the time direction. But the thing is, there is no gauge field to move it. Like the gauge field has two derivatives, right? So it's not just single derivative, so it just can't move. There's no way. So this one actually describes the fact. I should have used the blue color.
So I can understand this downstate as first you diagonalize, let's say one set of operators. Yes. Then on that, because it's not invariant to the others, you generate the X.
Exactly. Yeah.
More than
that's right.
Representation.
Yes. Okay. There are also these other defects of the other set of gauge fields that are they can bend only in one direction. So the I line bends only in the defect corresponding to that bends only in the I direction, can't bend in the other direction. So this captures the probability of the acceleration. that's just to give an example of these kind of models. This is not really what I'm going to talk about. I'm going to talk about exotic field theories. This is the main point of my talk. These are some features we have already seen Gramsci agency in the system already. Some other features include this. These are very non-relativistic. In fact, they don't even have like the rotational symmetry. So it seems like at least on the lattice there is a x going to y kind of like 90-degree rotational symmetry. Even the continuum theory has only that. Doesn't have like continuous rotational symmetry.
Sorry, I thought you said like the theory could be as a relativistic.
Exactly. So nice question. Yeah. So the toric code can be defined on any triangulation of the line, not just the square lattice. So on the lattice, that's how you see that it has complete rotational weight or relativistic weight. But this model can't be written on any triangulation of the line. It's like particular to this thing. There is people call this the foliation structure. Meaning your space has some foliated structure, meaning you have some planes which are special, and your symmetries act along those planes because of the subsystem symmetry. And if you can have a manifold which has a foliation structure, then we can write this model on that. But that's not true for anything. For example, on a sphere, you don't have foliation, so you can't write this on a sphere. Yeah, torus is very nice in that sense, right? All these things are torus.
So your tensor or whatever theory which I haven't understood, that you capture this the cubic whatever you described it, that would not be a relativistic.
Yeah, this won't be relativistic.
And you say not even rotational.
Yeah, not rotational. People understand this as a manifestation of this foliation structure. So if you want to preserve the foliation, you can do only 90-degree rotation. And yeah, more importantly, many of these exotic theories involve like discontinuous field configuration. I'll give an example of this prediction. It's hard to see why, but I'll soon give an example. And as we saw, there are exotic global symmetries like the subsystem symmetries, and there are also dualities between these theories. And
just one question.
Yes.
More of curiosity.
Yeah.
So these models exist in higher dimension.
We can, yeah, higher dimension. Like lower dimension and higher dimension.
No, but you had some X and Z operators.
Yeah.
Volume.
Yes.
Then in higher dimensions, what would
you can put them on plaquettes or you can still put them on lines. You can construct a lot of models.
I mean, you can think of that as an internal SU. Explain that.
No, I think the model had that, right? It depended on. Oh, so you will write exactly the same kind of thing.
Yeah.
On the hyperplanes, you will put that.
Yeah. And so there will be, let's say in 4 dimensions, there will be 6 hyperplanes. 4 choose 2 possibility. So instead of 3 vertex terms, I will have 6 vertex terms. And then I can write a cube down, hypercube down. You can do that.
But then the story code is some basically just continuation of that P code.
That's true. That's true.
But then the phenomenology is so different.
Exactly.
So that means in higher dimensions, the phenomenology, fractals, everything and whatnot, excitations, etc. would be very different.
It's very different.
But the model looks same.
Model looks similar. Exactly. But if you kind of see the pattern, in torical, you have like finite motion. Now in this one, you have 2 to the L.
Right.
The next one, I think you'll see 2 to the L square.
I see.
And it goes on with that.
Yeah.
And what would the analog of fractal be in one higher
The hypercube.
It's always points to the gauge variance of sigma x and then the
Yeah. You can construct other models, but this seems like a natural generalization of this one.
But in theory code, we don't have that.
No, because everything can move.
Yeah.
Yeah.
Suddenly, fractal amperes is 2, 3,
And then I don't know what happens. Yeah. I don't know the phenomenology, but some restricted mobility will be. So yeah, we have seen already this. Okay, I'll say internal degeneracies because when you look at the CN tensor gauge theory here, which I mentioned here, we talk about it. In the continuum level, we could take the LXL LZ to infinity, right? Like there are infinite in size. So the Gramsci degeneracy blows up. That's why I say infinity. There are also some divergent energies and such. The main question of this talk is how to make sense of these things.
And in the models that we talked about, what was the exotic symmetry?
The subsystem symmetry.
Generated by these line of
Just sorry, I was away. The subsystem symmetry. What do you mean? Numbers on play.
I'll soon get to that.
Oh, you get to I thought we were.
Yeah. So today I'll focus on like two theories. First one is an exotic theory, which we call the 2+1d5 theory. It has this Lagrange, where there is a standard kinetic term, the time derivative, but a non-standard spatial potential involving two derivatives or four derivatives. So it's usually two quadratic derivatives. Okay. Yeah. And
yeah, so we see the lack of rotation and that.
Exactly. And you should also see the subsystems. Yeah, I'll get to that. And just to help understand like these theories, I'll also talk about the 1+1D compact boson. That's like something that we all know, right? Like, so I'll first talk about the 1+1D compact boson, mention its properties.
The relativistic ones.
Yeah. The C equal to 1 CA.
Right, that second term we did, occasionally wherein we using the epsilon symbol, epsilon alpha beta del alpha del beta, just on spatial directions 5. So
that would be identical.
Yeah, it would be 0. It would be 0.
yes.
No, but nevertheless, it could be. I mean, looks like a boost in there. EBDU kind of. I mean, formally,
there will be a du squared and a du squared.
Okay, right.
So first, let me just look at the properties of 1+1D compact boson. So this is the Lagrange. It's a quadratic, it's a P theory, and the boson is compact, so it has this identification. The global symmetries include momentum symmetry or the shift symmetry, where you shift the field scalar field phi by a constant, and everywhere. That's important. And there is a Noether current for that.
So this is not in 1+1.
This is 1+1D compact boson. This is the standard ordinary theory. And there is a winding symmetry. It doesn't have a simple local action on the field, but you can write down the current. That's also conserved. There is a scale invariance in the problem. Yes, beta here is dimensionless quantity. And there is translation invariance and all. So this is like the simplest theory that you can do. And there is a nice cut-off anomaly between the momentum and winding symmetries. And as I don't know, there is a T duality where the theory at beta and theory at 1/2 beta is the same. And under this duality, the momentum and winding symmetries are exchanged. Everyone knows it.
This mixed proved anomaly is this the same as saying this, the operators that create momentum and the operators that create fine features of the
Yeah. We can also say this in the JJ correlation.
I see, no, because otherwise, if you look at JJ, I've never done this. J tilde J, that thing, where you look at as the standard kind of.
Yeah, exactly.
I guess there's an epsilon symbol. So it's not so strange.
This U1 point is in the text.
Sorry.
I mean, I think this module is a coordinate material.
Yeah, I'll talk about it.
And this U1 point
It's not there in the X1 model, but I'll talk about it.
So is it natural that this module
In some cases, yeah. So the X1 model has a gapless space in which its low energy physics is described by the compact boson. So yeah.
I think there is gap.
Yeah. There it's not described by this theory. It's not. Yeah.
And not this duality next.
Yeah. There's no duality.
And no this can only next.
No one. Yeah. I will talk about all of that. So, and let me now talk about the exotic theory. This one, we have the standard.
I'll just make sure I understood what Sanjeev said. So there's a U1 Kashmiri algebra for LX, for left mover, and the U1 Kashmiri algebra for right mover. And this one is like the one where the K's add up.
That's good. I just meant the diagram. and then you compute standard. Normally we try for fermionic products, but at the same time. Okay, that's what I low of my time. But okay, yeah, it doesn't matter.
So now let me talk about the exotic phi theory. Once again, you have the standard time derivative term and this non-standard spatial derivative term. There is a dual moment subsystem symmetry, and that is given by this. Like you have to shift phi by a function of x plus a function of y. But notice that it can be discontinuous. It doesn't matter because any discontinuous function is killed by this derivative operator. So there are discontinuous field configurations that are not suppressed by this action, that are not suppressed by this potential. You can think of this as like flat direction. Essentially, yeah, you have these discontinuous functions. You can also think of them like this. Why is it called subsystem symmetry? Let's say you have this system, x direction, y direction, and let's say the function c of x is some function of this form. So it's 0 here for these values of x, and some constant here for some range of x. What that means is there is a small region of phi that you shift by a constant. In the extreme case, you can make this width arbitrarily small. So it looks like you're shifting phi only along the line at a fixed x and nowhere else. That's why it's called a subsystem symmetry. Is that clear?
Can you say that once again?
Yeah. So let's consider a c of x, a cx of x, which is of this form, a function of x. It's zero everywhere except it's a small range of x. What this means is you're shifting phi by some non-zero constant only in a small range of x.
But everywhere in one.
But everywhere in one, exactly. So in the extreme case where this width of this thing goes to 0, it's as if you're shifting phi only at a particular x.
You're choosing a delta function for this.
It's not a delta function though, because we want this to be finite. This is just a function. So it's a very weird function. It's a discontinuous function. It's just 1 at a point and 0 everywhere else. That's not the delta function. It's more like a canonical delta.
Sounds like nothing. If it's just 1 at 1 point.
Yeah. But yeah, it's included in this.
Okay, fine.
But why is something subsystem? Because for the subsystem, say everywhere in y at this point in x.
Yeah. Yeah. This is called a planar subsystem. Okay. In this case, it's line because in the spatial manifold, it acts along a line. So it's called a linear subsystem symmetry. In 3 dimensions in the XP model, it would be called a planar subsystem. You can have fractal-like subsystems, but I'm not going to talk about those.
Already the fact that you're talking about shifting at a point by a finite amount tells you you're not looking at reasonable functions.
Yeah. That's what I meant by discontinuous field. It's very non-standard. You can also construct the Noether currents for this symmetry, for the momentum symmetry, and they satisfy this conservation equation. Notice that it has 2 derivatives on the it's not a single derivative. You can again, once again, like in the compact boson, we have a binding symmetry as well. It doesn't have a simple local action on the field, but you can write down the currents, and they satisfy again similar conservation equation.
Now we are in 3.
No, this is 2 plus 1D.
Yeah.
This is all 2 plus 1.
I mean, the compact boson was in 1 plus
1 plus 1. Yeah.
Nevertheless, we have this one.
Exactly. Yes. And there's also a notion of scaling variance where you scale x and y differently, but you scale tau by this product of lambda x and lambda y. This is a very non-trivial scaling variance that this theory has. Not like a standard scaling variance.
What is the scaling variance? What is that?
Lambda x and lambda y are just constants.
Oh, I see.
Yeah, they're the scaling constants. And this theory is invariant under this scale. Notice that this V naught and mu, I didn't mention this before, but they have mass dimension 1. Like if you just use the classical, the usual mass dimension, they would have mass dimension 1. But under this scale, they don't transform. They're just space. Okay. So the classical notion of scaling doesn't apply, but it still has some other kind of scaling.
So given that the fluctuations are not suppressed at all, it makes sense when you add a little bit of interaction.
Yeah, I'll talk about that maybe in the next lecture. Hold on to that question. The simplest answer is these nodes which are charged under this operator and duality, they have infinite energy. So even if you add such operator, they just don't act in the low energy space. So yeah, it's robust. And yeah, as I mentioned, this has translation memories, but it doesn't have a continuous rotation. It has only a Z4 rotation where you do 90-degree rotations in the XY. It has translation invariance, but it doesn't have a continuous rotation. It has only a Z4 rotations.
And here was your phi compact.
Yeah.
And
it's more complicated than what I would do.
Okay. But there's no, we haven't yet talked about winding, have we?
I mentioned
Winding.
yeah. In fact, these momentum and winding subsystems symmetries, they have a anomaly, a mixed anomaly between them, which is why this is gap was. You can see that in the current interpretation. See it then. And it also has a self-duality. So the theory with parameters mu and mu and rho, you can exchange them and it would be the same thing. Yeah.
You can see the total charges for the momentum.
So these are the
I'm not seeing how they use. Sorry.
this one has theta, the J.
Yeah.
This one has so I think I will just this is PX. This is theta. Yeah. This is the yeah.
Otherwise, your J tilde was
Yeah. That was a mistake.
Okay, thank you.
So this measures the winding in the X and Y.
Yeah. It looks like that JXY.
Which one? Yeah, this one looks exactly like that. And that's the duality. Under duality, these currents are exchanged. It's exactly like in the compact boson. The compact boson, we have the either currents for the momentum and then the winding.
Oh, the conservation equation.
Yeah.
What is the equation?
So the conservation equation is this. It's the same here, but actually these conservation equations are not the same. This one is it is trivial. This one is like a Bianchi identity.
Yeah.
But this one is the equation of motion of fun. Yeah.
And there's only one spatial JXY.
Yeah.
Even though in two spatial dimensions, there's one spatial.
That's right. And that's why there are lots of symmetries. Like for each X, you have a symmetry operator extended along with the Y direction. And for each Y, you have a symmetry operator extended along with X direction. These are the subsystems.
Sorry, you say what the unity exceptions are.
Oh, no, I didn't mention it here. I'll talk about it in the next one. So this talk is only about kinematics, symmetries, and dualities. Dynamics in the next lecture.
I'm sorry, one more time. If I integrate that over space, I get something that's non-zero only if something if phi winds in both exams. Yeah.
Yeah, it has to wind in both X and Y.
I see.
Yeah, if it winds only in X, it doesn't have it.
Yeah.
In fact, it's a weird configuration. I can write it down.
No, but so it's like a diagonal wrapping.
Something like that. So, yeah, let me quickly summarize these two things, compare them side by side. This compact boson on the left side and plus on the IKA on the right side. They look very similar if you look at these properties. They're both free. They both have some momentum and winding symmetry. They both have some sort of scaling variance. And these momentum and winding symmetries have anomaly, and they also have a self-duality. But as we discussed, there are discontinuous field configurations and just doesn't feel like nice to have that in the theory. Right? You would just exclude these things, like if you were really being conservative. So my plan is to place these theories on a lattice to regularize these discontinuities and in some sense make this analysis more precise. So that's the plan for the rest of the talk now. So I'll first demonstrate this thing and a compact boson and then do it in 5 years. For compact boson, it doesn't really matter, but I just want to demonstrate it. So that's where this XY model comes. Okay. So what we have is a Euclidean space-time, 1 plus 1 dimensional. You have a field phi, e to the I phi, some one variable at every side, and you have this interaction, cosine interaction, along every link in both time and space directions. Okay. And there is clearly a U1 momentum symmetry. You can shift phi by a constant everywhere, and the action is invariant under that. So there is that symmetry. But there is no binding symmetry, so there is no anomaly, there is no duality in the example.
Time is also.
Yeah, I'm assuming Euclidean space. Okay. Both space and time are treated equal. The thing is, when beta is very large, large scale fluctuations of phi is something. Right? So it's really described by the low energy phases described by the compact boson. It's gapless. So for large beta, the compact boson is a good description of the low energy. So there is an emergent binding symmetry in that case, and then there is a mixed anomaly which explains why it's gapless. But for small beta, as you go to smaller beta, starting from larger beta, there is a BKT transition where the binding operators become relevant. And so this model is gap. This model is gap. This is this binding operator. Not phi. The binding of e to the I phi the dual phi. That operator becomes relevant at small beta. So there is a BKT transition, and the model becomes gap. Okay. But the thing is, I don't want to work with a very strongly interacting model. I want to work with some quadratic theory. So instead, I want to work with a Venn representation. This model has the same phase diagram as the original XY model. So for large beta, it is close to a gapless space, and for smaller beta, it's a gap. It has a gap. And in the given model, we introduce these integer gauge fields. They are integer value, like standard gauge fields, but integer value. There is even an integer gauge symmetry, which ensures that phi is compact, because originally the field phi was compact. This integer gauge symmetry ensures that phi is still a compact. But the phi here itself is a real value field. It's different from what the phi that I had before. That was compact, that was circle value. The phi here is real value, and the integer gauge symmetry ensures that it's effectively compact. Okay. But this is still not good enough because the phase diagram is same as the XY model. It doesn't flow always to the compact boson. It flows to that only at last. So I want to modify this a bit. The problem here is the vortices. This model has vortices which proliferate at small b. That's why it gets gapped. What I want to do is suppress these vortices. And in this case, the vorticity is measured by the field strength of the integer gauge fields in every planet. This is what measures the vorticity, and I want to just suppress all the vortices. I can do that easily by using a Lagrange multiplier and just imposing it as a constraint. Here. Notice that this makes us very nice. Like you can manifestly see what the binding symmetry acts on. So the momentum symmetry now acts on the field phi, just shifts phi by a constant. The binding symmetry acts on this Lagrange multiplier field that I introduced, phi tilde, shifts phi tilde by a constant. So in the continuum theory, it's like we don't see that. You have to go to the dual effect to see the binding symmetry action, but here you can see both manifest. You can also construct the Noether currents for these and they have their own conservation equations. You can also have this anomaly between these U1 momentum and binding symmetries on the lines. Okay. And this is related to the fact that, like intuitively, that e to the minus of the action is invariant under the global symmetries, so the Lagrangian density is not invariant. Meaning, if you look at just a particular term, let's say this particular term at a particular location, and you apply the binding symmetry of the binding symmetry, this term is not invariant under that. But globally, it is invariant because this thing is a total derivative. It just adds up and it becomes zero. So this is in some sense the reason of why there is an anomaly between these two. People say that you can't realize anomalies on the lattice because any symmetry action which has anomaly would act would not have an on-site action. Here, what we have is an on-site action, both phi and phi tilde are completely local. They are acting locally, and still we see the anomaly.
So, sorry, it's very interesting. I've never, didn't know you can understand anomalies like this. But yeah. So, if you then try to redo the other procedure in this case, because the gradient is not in there.
Yeah.
You pick up an extra term. Is that how you see the current non-conservation? Maybe you have to turn on some background. I mean, how does it totally work here?
It's easy to see this by turning on the background. Yeah.
In the background,
you can add like gauge fields, background gauge fields, and you can see the anomaly there. You can do that you can do everything on the line.
but I mean, integrally tied to this way of thinking anomalies that the action is invariant, but not the
Yeah.
But usually that means you shift by a total derivative, shift the current. I mean, action being invariant, but up to a total derivative just spoil the fact that it's a symmetric. You add an extra term to the current. But here you can't do.
Yeah.
So something.
you're right, you're right.
And continues this step of action of your continuum theory. You can write this in continuum, so right?
Yeah, you can
So
take
you can model the
continuum
complex boson. Yeah.
Yes.
But wait, you suppress the vortex.
Yes.
The usual continuum compact boson has it.
So you can go back here to this action and add something like lambda cross phi tilde. You can get that vortices if you want. You just add these terms.
Right. But what is the continuum limit of the theory without the vortices?
You can do a compact boson.
But the normal compact boson has vortices. What do you say?
You have this operator, right? You still have this operator.
Wait, so the normal, let's say I've got my periodicity small enough. So normal compact boson has a Redmond operator, which comes from the vorticity. Right? This theory, as far as what I understood is this theory does not have such a.
Yeah.
So then how can they be the same?
The compact boson doesn't itself have a vortex, but you can add.
But it has a relevant operator.
It has a, even here you have this relevant operator, the alpha.
I see.
This is still there.
I see. So you remove what you thought was what is. I see. So then what is the advantage of this?
Yeah, what is it that you suppress this vorticity and why there's some transition and avoid the theory being gapped?
Exactly.
But if you have relevant operator as Shiraz said, why doesn't it?
I think it's ensuring the fine tuning.
Yeah.
That you have even in the lattice,
Yeah,
not turned on that branch.
Exactly. Yeah.
Otherwise, you do a latticization of this thing, and you will have an infinitesimal component of the relevant operators. You will never flow down to this one.
Exactly.
What you're here doing is ensuring you're flowing to this thing, even though it happens.
Yes.
So that's like basically getting the symmetric, right? To make this.
I mean, I would say, you're trying to arrange for a flow to a theory with a relevant. Yeah, like I said, yes, I agree.
You're arranging for a new symmetry so that it is not generated.
Right, exactly. This vortex operators charged under this winding. So if you preserve winding exactly, you will ensure that.
Then you can find.
This is infinite. Infinite.
Yeah.
Close it. This anomaly means that the long distance is described as a compact boson for all beta. There is no BKT transition because I suppress all the words. The infinite point.
So just let me totally understand. So I thought you were adding the Lagrange multiplier in order to get rid of the vortex.
Yes.
But because you added a new field, you added a new degree of freedom and had its own vortex. Okay.
Okay. So now this theory also has self-duality, exact self-duality on the lines using the Poisson distribution formula. Like you just do it for the integers, the integer gauge fields that I have. You would replace the ends with the integer gauge fields for the 5 tilde. We call them n tilde. So you can you can do exact duality, self-duality on the lines. So just to quickly summarize, we had the XY model, which was interactive. But on the other side, we have a compact boson or the modified Villen, what I call the modified Villen, which is completely free. The XY model had only the momentum symmetry, standard shift symmetry, but the modified Villen model has both momentum and winding symmetries. And there is no anomaly on the XY model side, but there is an external anomaly on the other side. There is a BKT transition in the XY model. There is no BKT transition this time. And
Really confused. I thought you can define a winding current in the X1, right? You have that current, right? You have the J, the momentum, the winding, and
so that involves this integer gauge field. Like, I don't think it's highlighted in the X1 model.
those comparisons are on the lattice.
On the lattice. Yeah.
Oh, okay, sorry. Okay, go ahead.
Yeah.
Okay.
So I could compare those one, but really the comparisons with the X1 model and modified it. And you don't have any self duality in the X1 model, but there is a exact self duality on the lattice in the modified it.
This is basically you're arguing that modified Wilhelm model is a good lattice version of that rather than that.
For the continuum theories. Exactly. So the purpose of this is in the exotic theories, you have all these continuities and finite energies. But once you go to the lattice, these are all regularized. So what is a good lattice theory that regularizes the continuum? That was the point.
Is this modified Wilhelm model something standard?
No.
I never heard of it.
I've not seen it in.
Yeah, it's beautiful. It's beautiful.
You know,
Because usually people probably use this X1 model.
yeah. So
Yeah,
people go to
The modification, the modification I've never seen before. It's fire.
yeah. So there was one other paper before us which tried to discuss this theory.
yeah. So
They wanted to add.
this is just a topological
I don't
interaction.
think so. That is the reason it's of exotic.
I mean, this stands for that.
I mean, normally, I guess this first term is.
Yeah, the Wilhelm model is very standard.
Yeah.
But then it adds this to suppress the vortices.
Yeah.
That I've not seen, and then recovers the vortices. I've never seen.
So now I want to do the same thing for the phi theory, the 2 plus 1 phi theory, the exotic one. So even here there is a analog of the XY model. It's called the XY bucket model.
No, sir. Maybe this is something good. So write this in continuum. Then they should have standard set of symmetry, right? The full conformal symmetry.
Yeah.
Of the
Yeah.
compact.
Yeah.
And then it looks a bit different on is just, you know, if you look at it because there is two fields.
Yeah.
Central charge, etc. seems a little bit different the way both are. But how because of the gauge, one additional gauge field, it reduces 2 to 1.
I think so. Yeah.
So I have seen that pure XY model does not have this kind of description which but if you have XY model plus a kinetic which gives some something like some constant times d tau pi whole square plus the XY term. Then there are two basically there are two parameters, one that appears with a kinetic term and one which is the parameter in the XY term. Then there is a self-dual point. So basically, if you have this kinetic term dominating everything, then the phase runs away. And if you have the XY term dominating, the phase is frozen.
Okay.
And the charge, the conjugate degree of freedom runs away. So this is often used to describe lattice superconductors. And the self-dual point is when the two coupling constants match. Like EC and BJ, let's say the charging or Coulomb blockade term and the Joseph cycle, they match. So then it reduces to precisely this new lattice model. So that is studied in detail. So it's a lot of literature in the 80s and 90s on this. Fazio and Schoen and many others have very long reviews on this. So, for example, at the self-dual point, you have very interesting new physics coming, but on the two other sides, you have very straightforward XY models of one or the other degree of freedom. Like sometimes you have phase as the right degree of freedom, and sometimes for charge and vortices. And then there is a topological interaction, which is I times Q dot times V. Then V is the vortex, Q is the charge. So I've seen these things before. But pure XY doesn't have it. pure XY on the lattice just doesn't happen.
Yeah.
So just to make sure, the continuum description is in either in terms of phi or in fact.
Yeah.
No,
Yeah.
there's no continuum with both.
Yeah.
Why not? Sorry, why can't you just take this case it is modified rather than continuum?
Yeah. So the you would still have the integer gauge fix. So we want it as gauge fix now. But nice way to do that is integrate out the phi tilde. What it does is makes the gauge flow flat. So and then you can gauge fix the n tau and nx. Essentially, what it gives you is the holonomies of these n tau and nx. They become the winding charge in the continuum. So the phi tilde is gone on the lattice, and you gauge fix ends completely to be almost zero everywhere except in some corners. And then you can take the continuum. You get just you get immediately the compact goes on. Yeah, I can explain this like after the lecture. I don't want to go through that, but you can do this exactly.
So, but I cannot write the continuous model where I can see both.
Yeah, I don't think so because I don't know what
Because the
ends
ends.
do. Yeah,
Because of the same.
Ends.
yeah.
What are the
Because
ends?
they're discrete.
In the context of T-duality, people talk sometimes about this double definitely. Where they introduce two degrees of freedom. So it very
Oh, yeah. It's very similar to that. Yeah.
Then that is continuum discussion.
So there, the way you do it when you introduce phi tilde, you have to forget about phi. You introduce a new variable for d phi.
Yes. Okay.
So I don't think you have phi anymore.
Double means I thought double. But okay, I personally have not studied, so I cannot say much more about it. But this sounded similar to that.
I don't know.
But yeah, please.
There are also these self-dual theories of superconductors in the competing with some Coulomb terms, and there also you get these mixed type of terms and theories because the interaction between pieces and pairs is converging. And so they are also like you easily go to these continuum limits where you take both the vertices and charge pairs together, and you have gauge theories described.
Okay.
So are they how you have it?
No, I haven't seen. Let me move on to the XY bucket model. Once again, we have Euclidean spacetime now, two spatial directions and one time direction. And I want to place a U1 variable at every site. And the action is this. We have a standard, the position XY type term that we had before. But the other term, the potential term is del x del y phi. So what this means is, let me just draw this. You have a square lattice and you take phi's live on the sides. So you take phi here, minus phi here, minus phi here, and phi here. That's what that term is. And this you add. That's what this term is. And this was originally studied in the Hamiltonian formulation by Pranay Gorantla, Fisher, but I want to just stick to the picture. And clearly, this thing has a U1 subsystem momentum symmetry, where I shift the field phi by a function of x plus a function of y. And here there is no issues of like functions being just one at a point. You can have like one line where the field is shifted and rest it's not shifted. So clearly, this is a subsystem symmetry, and it all makes sense. It's fine. There's no discontinuity here. And there is no winding symmetry though. So there is no anomaly and there is no self-duality. And yeah. And for large beta node and beta, the gapless, it has a gapless phase and it's described by the 2+1 I'm not sure what happens when the betas are small. I mean, people are still working on it. We don't completely understand what's going on there. For large beta. So once again, we can go through this route. First, villainize it and then modify villainize it and write this action here. So you have the kinetic term with a gauge field and tau, the temporal gauge field, and then we have this potential term that deals with an xy, and finally we have this term which suppresses the vortices. In this case, the vorticity is measured by this. It's not like the standard vorticity, but still, this would be the natural analog of what we were doing before. Okay. And the fields phi and phi tilde here are in real value, and the n tau and nxy are integer value, and they have this kind of an integer gauge. So both phi and phi tilde are effectively compact because of this integer gauge symmetry. But notice that the field nxy here has a non-standard gauge symmetry. It's del x del y gauge.
Sorry, nxy, could you tell me, just show me any R there?
So
in the previous case, this model, this compact Poisson just cannot write it down, cannot discretize it without kind of and preserve all these nice properties without going to this modified Villen model.
yes, yes.
Okay.
So nxy is like one unit joint binding x and y.
Something like that.
Okay.
Is something like that. This is an example of a tensor gauge field. Here it's integer value, but the gauge symmetry involves like 2 derivatives. That's why it's
So roughly, why is that the case? Why can't we usually when we go from we have a discrete theory and then want to have a continuous theory, we just simply kind of discretize it, try to write down the action on some discrete lattice. So is this like a general thing that we cannot quite take continuous field theories and just write in a nice fashion?
When they have relevant operators, you might trigger the relevant operator.
And that is what is happening in this course.
In this case, it has a relevant operator, you're triggering it, so it flows away from it.
And why doesn't that happen in this continuous case? Because we have some symmetry.
Yeah, you ensured that the relevant operator is charged under minus.
yes.
You ensured that is present.
No, but exactly. But in general, when the symmetry is not of winding type, it's a topological type.
Then you have to do a cube.
No, I can ensure that symmetry is present on the lattice also. Why can't I, in general, not do
But
that?
suppose you've got a relevant operator which is not switched off by symmetry. Like in Wilson-Fisher theory, for instance. Okay, you want to reach the Wilson-Fisher theory on a lattice, you'll have to do our one parameter tuning. You have to have a one parameter set of lattice with parameters and hope that you get the fixed point with that one parameter tuning. That's what is the standard.
But I think, I'm not sure. Maybe what I did say is precisely because that operator was a kind of topological non-local operator. You could do it with these integers, It seems connected, right? It's very interesting.
It's very beautiful. I've never seen it. I've never seen it. I mean, pick it up. I've never seen it.
Yeah, but this is new.
Yeah.
Now this is right. Yeah. So I've never seen.
So that one was in the appendix. This one is in the main.
Yeah.
This is new for me.
So, yeah, so you're saying, sorry, just to observe this, that here you already see the meaning of a tensor gauge.
Yeah.
It's like a double.
Yeah, exactly. Yeah. And these integer gauge symmetries make the fields phi and phi tilde effectively compact.
I'm sorry, I mean, it should be clear. Why did you multiply phi tilde? Why did you multiply that particular combination?
No, so this is the so these are the gauge symmetries, and this is the only field strand that we have. So here, I don't know if there is an intuitive picture like vortices. Like in the X1 model, we know what the vortices are, but once you turn it into an algorithm where you have these field strands of integer gauges and you want to make them flat,
I see.
then you just do that. Just follow your nose.
I see. I see. But do you suspect that in this theory there is some operator which turns on?
No, it is Wi-Fi cable.
Yeah.
So that's charging the divine symmetry. That will turn on the vortices.
Can you write down the continuous version of this model? So that it is recorded.
Okay.
So the,
Sure. Yeah.
Where you start.
Yeah.
like
The one with the
everything down to the next is like,
So one question here. Suppose I had, in addition to this dx dy by whole square, just dx square phi whole square.
Yeah.
That is not according to
wait. Did you mean dx phi square?
No.
Oh, you mean this one? Oh, okay. In this theory, so I didn't talk about this, but I didn't say what this gate symmetry was, but the gate symmetry is such that dx phi or dy phi, they are not gauge invariant operators. They're not invariant under this identification. So these operators are not there in the gate. So similarly, this one is just a higher order version of this. So these operators are not there in the gate. This is also related to the fact that I wrote the current here this way. Okay, and the current involves the two derivatives. You could ask why not write it as del x squared del y of something, which is dy phi. But the thing is that this operator is not there in the theory, it's not well defined. That's why you can't do that. Yeah.
Also, I mean, I suppose relatively, if this operator was here, to completely change the physics of your
Exactly. Yeah.
Because shifts in x would no longer be here.
Exactly. Yeah. And this would be more relevant than that. It's like higher order term, right? So it would flow to the compact both or something like that.
No, I mean, the dx square phi quantity square and nice power counting would be as.
Yeah. So if you want to add this, then then it's relevant. But if you add this, like this square, then it's.
No, I mean, once you have that, the symmetry will break and those things would also.
Exactly. This one actually, there is still a dipole symmetry that you can shift phi by a linear function in x. So this is suppressed by if you impose that symmetry. But if you don't want any of the symmetry, you just want the constant shift, then you can add this too.
That second one by itself without your that's a standard shifts.
This one, yes, yeah. So yeah, I was here. So yeah, now we can look at the global symmetries. Like it's very apparent. You can shift phi by a constant in x plus a constant in y. You can sorry, a function of x plus y. And similarly, phi tilde you can shift it by a function of x plus. Quickly show why. So this term is clearly invariant because you have some derivative time sum over all the time it's invariant. This term involves two derivatives, delta x and delta y. So that will kill the function of x plus function. So it's still the same. And again, you can realize the anomaly between the momentum and light symmetries on the lattice. Then you can also see the self-reality on the lattice for some reason for the integer. So let me quickly summarize. So we started with the XY plaquette model, which was an interactive theory and had only a momentum subsystem symmetry, and has no winding symmetry, no anomaly, no exact symmetry. But then we do the modified Williams procedure and then create a free theory, which has both the momentum and winding subsystem symmetry. And it realizes the anomaly and has an exact circuit.
So just coming back to this anomaly on the lattice, this business about shifting by a total derivative. Could it be that the total derivative is not invariant under the other symmetry? This is why. So you were saying that the way it works is that the action is not invariant, but it's invariant under up to a total derivative.
Yeah.
So now if we study the total derivative, is that total derivative charged under the other symmetry?
Actually, the action is invariant in space.
So the action is invariant. Sorry, the Lagrangian.
The Lagrangian is not.
That's right. Yeah. So the Lagrangian is not invariant, but it shifts by total derivative.
It shifts by a.
And the total derivative, is that charged under the other symmetry?
No. Yeah, that's also what we have talked about. Like you can apply this modified Williams formula to other ordinary and exotic theories. You can do clock model, CN gauge theory, one gauge theory in any dimension and any form. You can do it for P form stuff. And you can also repeat it for like exotic theories, like the free thing for the XQ model. You can do it for that. You can do it for XIV series and other calculus models several times. You can do it for any, like at least all these kind of models. And in all these cases, these models are nice because they preserve all the exotic globals within the continuum theory mass. It provides like a new nice regularization of the continuum theory. And yeah, it provides a rigorous treatment for all these continuous field configurations. So infinite indices, all those things. All of them get regularized and become fine. Okay, next time I want to talk about the dynamical aspects, which I didn't talk about today. I'll discuss the spectrum, energies, and correlation functions of some operators in the theory, and how UV analysis manifests in this correlation.
It's for the model, these models.
Yes, this one. I'll do it for you.
And when is the next?
Yeah, we have to decide that. This is based on Rajdeep.